Start recording. All right. So today is going to be a little math intense. So, well, not technically math intense, but the process you will see that we follow to find the vibration or response of a 2 degree of freedom system to some initial velocity, initial displacement is relatively long compared to what we were doing for 1 degree of freedom system. So bear with me, follow the steps. It's very straightforward, and I'll give you a step-by-step process how to do each step and get the final response. All right, just as a heads up. All right, so here's what I want to do. So we talked about mode shapes and natural frequencies, right? Eigenvalues and eigenvectors. We said as long as we can find the mass matrix and a stiffness matrix, as long as we can find the equations of motion and right in a matrix form, we're going to have our mass matrix and a stiffness matrix. Right? Knowing these two matrices, we can use eigenvalue problem, form the eigenvalue problem, find eigenvalues, which as a result give us natural frequencies. We're going to have 2 for a system with 2 degrees of freedom. And from there, we can find eigenvectors, which basically are mode shapes. Now, here is how we use those information, like natural frequencies and mode shapes, to analyze a vibrating system with 2 degrees of freedom. So we're going to start with free vibration, meaning that there is no external force. And as I said, within the scope of this course, we do not talk about damping in systems with 2 degrees of freedom, only spring mass systems. And we'll see how can we actually use what we learned to find the system response. So that goes under free. Let me move things around a little bit. All right. Free vibrations. Free. I guess that's morning. It takes some time to get used to the board. Free vibrations of a 2 degree of freedom system. How do we do that? We're going to use the procedure or the method called modal analysis. Now, modal analysis is a field by itself. There is experimental modal analysis that they do to test big structures from airplane wings to car bodies and different parts to find natural frequencies and mode shapes. When they're designing structures, it's a very important step because you need to know the natural frequencies and the mode shape of the structure to be able to design the whole system properly. You have to avoid resonance, you have to avoid specific frequency ranges to make sure your system operates I would say properly and within its best, I would say, operating condition. Now, so we're going to use that method. It's a simplified version of that. We just apply it to a system with 2 degrees of freedom, but the same approach can be followed for systems with as many degrees of freedom as you have, right? 10, 20, thousands of degrees of freedom. As a matter of fact, again, as I said, I think before, that a lot of commercial software packages, that's how they do calculation and, well, general procedure. The computational aspect is a little different, but the procedure is the same, and that's how they find natural frequencies and mode shapes for you for different parts when you are doing vibration analysis in those software packages. So free vibration of a 2D of system, and we are gonna, let me just write a few lines. So we to find the system response of a 2 DOF system under free vibrations, we use modal analysis. I can do better analysis. Modal analysis technique or method. So we have to discuss what that technique is, or what is modal analysis. Let's just start here. So modal analysis, I'm gonna put it under modal. I don't know, for some reason my handwriting is not great today. Modal analysis. So, modal analysis. Do you remember when I talked about mode shapes and natural frequencies? I said mode shapes, you can think of those mode shapes as unit vectors, like the same way that you represent any vector in a space, like two-dimensional space, you represent the vector or vectors, any vector using I and j, right? Those unit vectors that you have in Cartesian coordinate system. If you're in 3D space, you represent any vector with 3 unit vector, I, j, and k, right? The combination of these 3 can represent any given vector, as long as you know the magnitude of the vector in each specific direction. The same story applies to modal analysis. Now, in modal analysis, we say we can represent, it can be proven mathematically that we can represent the system response to any given input as a combination of mode shapes. Right? As long as we know the mode shapes and natural frequencies, we can represent the system response as a combination of those modes. So as long as we know for a 2D of system, as long as we know the first mode and second mode, which includes mode shape and natural frequencies, we can represent any response to any input with those. So here's what we I would say approach. When omega is omega 1, right? When the system is oscillating with its first natural frequency, remember that. We are in the first mode. We are in the first mode. And we have, you can say we have x 1, 1 and x 1, 2, right? These are mode shapes. When omega is omega 1, we said the ratio between amplitudes, x1, and x1, 2. Now, when omega is omega 2, we are in the second mode, right? And as a result, we have x21 and x22, right? Second mode, second natural frequency mode shape. Now, when the system is oscillating with any other frequency that is not either of these two, right? Let's say the first natural frequency is 10 radian per second, the second is 15 radian per second, or 20 radian per second. We have 10 and 20, and the system is oscillating in 15 radian per second. It's neither first nor second. At any given frequency, the way the system responds to the input, in this case the free vibration, so some initial velocity and displacement, can be written as a combination of these two. So I'm going to write it here. The system response, let's see if I have a better wording there. Yeah, that's pretty much the same thing. The system response can be written as a combination of these two modes, right? First mode and second mode. Remember that. We said this is this is first mode, this is the second mode. All right. So mathematically speaking, it means we're going to have system response, let's call it x1t, x2t, we have x11 first mode, x12, two components of the first mode, some harmonic function, you can write it this way, sine omega 1t plus phi 1 plus x21 and x22 sine omega 2t plus phi. Now, again, we can write it. This is the response from the first mode. This is the response from the first mode if it oscillates in omega equals to omega 1, and this is the response for the second mode if omega is equal to omega 2. Mode shapes multiplied by some harmonic input. This is free vibration, so we give some initial velocity or displacement. I can rewrite this. I can write it in this way. x1t and x2t is equal to, I can write it as x11, x12, x21, x22, right? And then write it this way, sine omega 1t plus phi 1, and then sine omega 2t plus phi 2. If you do this multiplication, this is a 2 by 2 matrix. It's a 2 by 1 vector, and it's a 2 by 1 vector. You'll get the same thing. x1t would be x11 sine omega 1t plus phi, and x21 sine omega 2 plus phi. You can just do the math, we get the same thing. First row gives you x1t, the second row gives you the x2t. I just rewrote this one in a matrix form. Now, we actually are missing some coefficient. I guess I have to put the coefficient somewhere because it has to be a combination of these, right? We said the combination of these two modes as a result, it has to be multiplied by something. Call this B1 and B2. Just B1 and B2 are constant, or just constant values, some number. Because we are forming the solution, and we say solution is a combination of this system response to the first mode and system response to the second mode. Which one has more effect on the result than the other one? It goes back to those B1 and B2. B1 and B2 are weights that we actually apply. So B1, if B1 is very small and B2 is very big, meaning that more contribution is coming from this second mode, less contribution from the first mode. And the same logic. If you have more contribution from the first mode, B1 is bigger. You have less contribution from second mode, B2 is smaller. We actually find that B1 and B2. Right? You actually don't know that. You just put it as constant there. So let me add them here, B1 and B2. So just constant. So x1t would be x1 1 sine omega 1t plus phi 1 plus B2 x21 sine omega 2t plus phi. The response of one of the masses. We have two masses. Right? x1t would be a response for mass 1, x2t would be a response for mass 2. All right, so now here is where things get interesting. This is the matrix form. I can write this. Right? This one is called, let me write it in a more concise way. I can write it this way. Xt is equal to psi, Greek letter psi, q t. It's the same thing. I just wrote it in a, this is still 2 by 1 vector. This is 2 by 2 matrix, and this is 2 by 1 vector. This is the physical domain. This is called modal domain, and this is we call modal matrix. Modal matrix. So what is this modal matrix? Well, we can form it by, as you can see, finding mode shapes. First column of the matrix is the first mode, and second column is the second mode. I have a system with 2 degrees of freedom, we have 2 modes. What does this do? This transforms, look at the form of this equation. It's a xt physical domain, the physical domain we have, x1 and x2, those 2 degrees of freedom, is equal to some matrix, modal matrix we called it, times some other vector. So this, the essence of modal analysis is basically a transformation. What it does, it transforms the coordinate system, in this case x1 and x2, to a new coordinate system. Call this one q1 and call this q2. Do it this way. Call this one q1t and call this one q2t. So it transforms the coordinates from one domain to another domain. How do we transform? We use modal matrix. How can we achieve this transformation using modal matrix? We go from physical domain that we know x1, x2 to modal domain. What is modal domain? It's a different coordinate system. Physically, you can't see that, but you go from one domain to another domain using modal matrix. Now, why do we do that? Well, first, let's say modal matrix would define these. So the modal matrix is formed by mode shapes, which are or eigenvectors, where the first column is the first mode, and the second column is the second mode. Right? Just as a reminder, this is a very important matrix. Psi, Greek letter, x21, well, x1, 1, x1, 2, this is first mode, and then x2, 1, x2, 2, second mode. First mode, second mode. Right. First eigenvector, second eigenvector. So why do we do this transformation? Right. You can add this to that mode, which these are eigenvectors found from eigenvalue problem that we solved. Remember, it was k minus omega squared m times x is equal to 0. No eigenvalues, we could find eigenvectors. These are eigenvectors. Now, the question that comes up is that, well, why do we do this? Right? What is wrong with being a physical domain? Why do you want to make a transformation and go from physical domain to some modal domain? I'll tell you why. Because when you're in physical domain, the equations are coupled. What does that mean? It means if you remember when we were looking at the equations back then, they were like m, for instance, m1 x1 double dot plus let's say k1 plus k2 x1 minus k2 x2. Then the second one was something like this, k2 plus k3 for some given system, x2 minus k2 x1 is equal to 0, something along that line. Now these equations were coupled. What does that mean? Well, look at them. The problem we have with these equations is that in the first one we have x1 and x2. In the second one also we have x2 and x1. So what is the problem? The problem is they're not separated. If I had something like m1 x1 double dot plus k1 plus k2 x1 is equal to 0, but I didn't have any component of x2 there, then this would have been a system of single degree of freedom system. Right? We studied this mass spring damper. This is basically just mx double dot plus kx equal to 0. We know how to solve this. Very straightforward. The problem with systems with 2 degrees of freedom or higher degrees of freedom, as a matter of fact, is that now you have a component added to this equation that is coming, or it couples this equation to the second degree of freedom, or both degrees of freedom exist in each equation. x1 and x2 exist in both. How can we solve a system with multiple degrees of freedom then? One way is modal analysis. What does it do? It decouples the equation. So what happens, you will see, I'm going to show you that once you make that transformation going from physical domain x1 and x2 to modal domain, they are not coupled anymore. You are going to get something like a new kind of m, though, called m11 q1 double dot plus k11 q is equal to q1, and then you get something along the line of this q2. Now the equations are uncoupled in modal domain, meaning that each of these is just the 1 degree of freedom system equation of motion for a system with 1 degree of freedom. You can solve that. We already know this. This is mx double dot plus kx equal to 0, and that's why we make that transformation. So we'll see. You'll see how does this work. Let me show you. So let's replace that. Let's plug in the equation star into the equation of motion. Equation of motion, and remember the equation of motion for a system with 2 degrees of freedom was m x double dot, I'll just keep it as x, just remember it's xt, function of time, plus k x is equal to 0, right? That was the equation for a system with 2 degrees of freedom. 2 by 1 is a 2 by 2 matrix, a 2 by 1 vector. Now let's plug in the transformation. I'm going to put the star here, this transformation matrix or process, well, relationship, modal analysis. This is the I would say fundamental equation in modal analysis. This is basically just a transformation. Well, let's put it there. If I do it, this becomes m psi q double dot plus k psi q is equal to 0. I just replaced x, right? This was the transformation. I replaced x is equal to psi q. X double dot becomes psi q double dot. Psi is just a matrix of numbers, constants. Now here's a little bit of algebra. What do we do there? We're going to multiply both sides with psi transpose. It's a matrix 2 by 2. The transpose of a matrix 2 by 2, just you replace, keep the diagonal and flip the elements, off diagonal elements, right? Or the formal definition, you replace the rows with columns. First row becomes first column, the second row becomes second column. If I do that, this becomes psi transpose M psi Q double dot plus psi transpose K, K is a matrix, K psi is a matrix too. Psi times Q is equal to 0. So why did I do that? I replace that. Why did I multiply it by psi transpose from the left? Well, if you do that, that gives you, this one is important and this is important. This, the outcome of this is called modal matrix, or modal, modal mass matrix, right? And this is modal stiffness matrix. Now, we can prove that mathematically. I'll just give you the general process, that what happens if you do this multiplication. There you go. Let's look at them separately. This is modal mass matrix. We show it with MR. Is psi transpose M psi. If you do that multiplication, that's the beauty of modal matrix. It always gives you a diagonal, a matrix with diagonal elements, off diagonal elements of 0, 0, 0, M, 2, 2 bar. So M1, 1 bar and M2, 2 bar are modal masses. The second one, modal stiffness matrix, modal stiffness matrix. So important concept, guys, pay attention. So now we are introducing modal mass matrix, modal stiffness matrix. The elements of modal mass matrix are called modal masses. First modal mass M1, 1 bar, and second modal mass M2, 2 bar. Modal stiffness matrix, KR psi transpose K, stiffness matrix psi, also gives you a matrix with only elements on diagonal, only diagonal elements. Call this K1, 1 bar, 0, 0, K2, 2 bar. And K1, 1 bar and K2, 2 bar are modal stiffnesses. So we have modal masses and modal stiffnesses. Now let's rewrite this equation. I got modal mass matrix, modal stiffness matrix. I know it's this now, and this one I know is this. Let's rewrite the equation. I'll show it like this. So I plug in these into that equation. This is a given. I'm just telling you that whenever you do this multiplication, you will get a matrix in this form, modal mass matrix, and this is going to be modal stiffness matrix. So if I plug that into the equation I showed with the square, you will get something like this: M1, 1 bar, 0, 0, M2, 2 bar, I'm writing it in a full form. Q1, Q2 double dot plus K11 bar 0, 0, K22 bar Q1T, Q2T is equal to 0, 0. Look what happened. Now, this is the equation of motion in modal space. Right? Equation of motion in modal space. We did the transformation. We went from physical space to modal space. In modal space, look what happened. These are uncoupled equations. So now equations are uncoupled. Now these equations are uncoupled or decoupled, depending on who you talk to. Uncoupled. Here what we have now, if you do the multiplication, first equation would be M11 Q1 double dot T plus K11 Q1T is equal to 0. And the second one gives you M22 Q2 double dot T plus K22 Q2T is equal to 0. Now we have a system that is uncoupled, meaning that the first one is just a single degree of freedom system, right? It's what you know from before. Mx double dot plus Kx is equal to 0. And the second one is also Mx double dot plus Kx equal to 0. It's very easy to solve now. You don't have to go through any other process. From here, you already know how to solve this. Solve this from what you know for a system with single degree of freedom. Right? Remember, for a system with single degree of freedom under free vibration, we had each equation is now a one DOF system. So we can actually solve this. So Q1T would be some constant A1 E2. Let me write it maybe down here. Q1T would be some constant AE to minus zeta omega 1 T sine omega D T plus phi. I have to double check the way we were actually solving this. I'm not sure if we're putting plus or minus. Actually, I can check it based on what I have. If I can find it. Q1T. Oh, actually, we don't have damping. Yeah, it's even easier. So we have Q1T as A. I don't know why they put the damping there. A1 sine omega 1 T plus phi 1. And QT would be A2 sine omega 2T plus phi 2. Right? Now remember, this should be solved with initial conditions that now you have in modal domain. Right? Q1 0 and Q1 dot 0, and this should be Q2 at t equals to 0 with Q2 dot at t equals to 0. You remember this. This is the system with single degree of freedom. I just replaced X with Q1. It's a single degree of freedom system, spring mass damper. So each is just a single degree of freedom system. So we can solve this. We can get Q1T and Q2T and then transform this back into physical domain. Now I'll talk about it in the example and how to do it. It's a very straightforward approach. Now, conceptually, here is what we are doing. Let me just emphasize this again. You have a system with 2 degrees of freedom. Right? This is just a spring mass damper system. Well, there is no damper, spring mass system. I'm not going to talk about dampers. Sum K1, K2, K3, and you have X1 and X2. That's what you have, M1, M2. Now here is what you are doing when you do modal analysis. You go and convert this into two single degree of freedom system. Right? This is the first system. The mass is M11 bar, it's a modal mass. And the stiffness is K11 bar. This is the second system. K22 bar, M22 bar. So you have now two single degree of freedom system in modal domain. All right, let me not put it here. For each, you find the system response. Here's what we get. You get the system response like this. Let's say Q1T time, and this is Q2T time. It's a free vibration, so for each of them you will get something like this. No damping in this case. You will get this, and let's use different color. You get this. This is Q1T, Q2T. Each response you get for a single degree of freedom system, you convert, or then you transform the response. This is the response in modal domain. Right? I'll write it here. Responses in modal domain. Modal domain. Now you convert that response, or transform it back to physical domain. You use mode for each one. For this one, you have with X1, and this is with X2. Using these two, use the mode shape, convert them back. You will see how do we do it in matrix form. And then you will get, just sum them up. You can do a better job there. Sum them up. You will get the response in physical domain, which is a superposition, not exactly just summing them up, because they have to multiply it by the modal vector, or mode shape. But then you will get the response, which is a response for your system. Right? You will get, let me write it this way, they're still separate. So it's easier to actually do it this way. So from there, you will get X1T, and you'll get X2T. Remember, these are, maybe it's confusing, these are not coming from them separately. This is just after you do the multiplication, and then you get these two. You get X1T, some response, and you get X2T, some response. So that's the general procedure. This is the idea of modal analysis. Go from physical domain to modal domain. So you uncouple the equations. When you have 2 degrees of freedom, you get 2 single degree of freedom. Solve each of them, and then knowing the mode shape, find the contribution of each response in the physical domain, and find the system response in physical domain. So there is one transformation to physical modal domain. Solve it there because it's easier. Then bring back the solution to physical domain. Now let me give you the procedure step by step. How do we deal with this, with a system like this, when we have an example in front of us? Procedure. There's some small steps there that you have to take. So step one, right, derive the equation of motion. Derive the equation. You have a system, you're given a system, and you're asked to find the system response for some given input. Right? So derive the equation of motion and write it in matrix form. Right? So we're going to end up having m x double dot plus k x is equal to 0. That would be your equation of motion. Right. Procedure. Let me add this here. To find system response to given initial conditions. What are initial conditions? Well, we have two masses, so each of them can have initial displacement, initial velocity. So x1, let's call it x1, x0, we'll call it, would be x10 and x20 at the beginning, and x dot 1 is x1 dot 0, x2 dot 0. What does that mean? It means you have two masses, you can give initial velocity displacement to each of them separately. You have initial velocity and initial displacement. So initial velocity would be initial velocity you gave to each mass. Right? I just push this one with 1 meter per second in this direction, the other one with 2 meters per second in this direction. And initial displacement, where did you let them go or push them at the beginning of the motion for each mass? So you're given initial conditions, the same way that when you were dealing with systems with single degrees of freedom. So first, derive the equation of motion, write it in a matrix form. Second, step two, exactly just follow these steps. You form the eigenvalue problem and find eigenvalues as a result, eigenvalues and let's say eigenvectors. Eigenvectors, which are basically or mode shapes. Mode shapes. We have what we get out of this. So this is the procedure: k minus omega squared m times x is equal to 0. From there, you get lambda 1 and lambda 2. As a result, omega 1 would be a square root of lambda 1, and the second natural frequency would be a square root of lambda 2. Now, for each lambda, you also get mode shape. For lambda 1, right, for lambda 1, let's put it as an arrow, you get x1, which is x1, 1 and x1, 2. For lambda 2, we get x2, right? x2, 1, x2, 2. So you get mode shapes. This is what we have been doing so far. The next steps are new, right? The next steps are next few steps are new. The first two that we've been doing so far, we could find natural frequencies and mode shapes. Now, form. Let's say form the modal mass. The modal mass matrix and modal stiffness matrix. That's pretty much it. So I'll write it this way. You say, well, modal mass matrix is equal to, wait, I have to form the, let's add this step, form, yeah, this is better, form, I can just add it to previous step actually, it's probably easier. So form and form the modal matrix. Always modal matrix, well, as long as you know mode shapes, you're fine. You can just say psi is equal to, well, x1 1, x1 2, right, and then x2 1, x2 2. This is your model matrix. Then we'll go to step 3. Now we can form or construct modal mass matrix and modal stiffness matrix. Similar to what we defined them. Modal mass matrix is psi transpose m psi. I'll just do the multiplication and you will get m1 1 bar 0 0 m2 2 bar. Keep in mind, always off diagonal elements should be 0 when you do this operation. And kr is psi transpose k psi, and once you do that, you're going to get a 2 by 2 matrix with off diagonal elements 0, and diagonal elements are going to be your modal mass and modal stiffness values. This is as a reminder for those of you who do not remember how to find the transpose of a matrix, 2 by 2 matrix. If A is A, write it this way, A, B, C, D, transpose is equal to A, B, and C, D. Hopefully I didn't make a mistake. A, B, C, D, first row becomes the first column and second row becomes the second column. Reminder, I'll put it here. So if you don't know how to find the transpose of a matrix, 2 by 2 matrix. All right, so if you do this, you're going to get your decoupled equation, right? You're going to get it as m11 0 0 m22 bar. Then you'll get q1 double dot q2 double dot plus k11 0 0 k22 q1 q2, and you'll get 0 0 there. It's decoupled equation. Now here are a couple of things that you have to do before you can actually do the transformation and everything that works fine. Now keep in mind, you are transforming, you are going from physical domain to modal domain. Now you're given some initial conditions in physical domain, so you have to transform those initial conditions also from physical domain to modal domain. Now how to do it? Well, you can actually do it using a modal matrix, but there's a step that you have to do before that. Not the same transformation you use x is equal to modal matrix psi times q, right? The same transformation you use to transform initial conditions from physical domain to modal domain. But before that, you have to normalize your mode shapes to get the right amplitude transformation from physical domain to modal domain. Now, how do you do that transformation? Normalization. Oh, we have to do normalize mode shape. So I'll show you how. Normalize the mode shapes with respect to modal mass. modal masses. So this becomes x1. I'll give you the process x1, and let's call it x1 normalized norm is equal to x11, x12, multiply these two by 1 square root of m11 bar. This gives you the x norm. x2 norm is basically just your mode shaped, x21, x22 times 1 over square root of m22 bar. So your normalized, I would say normalized mode shape, modal matrix, it becomes psi norm. This becomes psi norm is equal to x, let's write it this way, so 2 vectors. So let's write this x1 norm and x2 norm. Right, this is a 2 by 2 matrix, which you can write it like this. I'll use the x1 norm, x1 2 norm, x2 1 norm, x2 2 norm. All right, this was the new step. Now you can convert your initial condition. So now you can, knowing that you know the modal matrix, normalized modal matrix, you can use the normalized modal matrix to convert the initial conditions. So here's what you do. So take the initial conditions, take the initial conditions into modal space. How do we do that? The same transformation, right? The same transformation that we said is the backbone of modal analysis. X is equal to modal matrix times Q. Right? We just do it, we use that one. So using X is equal to psi Q. Now Q, if we follow those steps, right? X dot, so X dot also becomes psi Q dot. Initial conditions, what are they? They are X at the beginning and X1 at the beginning and X2 at the beginning. So you can pretty much just do that and follow the steps like this. So you can say, well, Q at the beginning as a vector is the inverse of this one, right? I'm finding Q as X. Inverse of the norm vector or matrix times X. And this transforms all the initial conditions. Same story about velocity, initial velocity. If you want to find them in modal space, norm X dot. Now you might be uncomfortable using inverse of a matrix, finding the inverse of a matrix. I would suggest instead of finding the inverse of a 2 by 2 matrix, you're going to have an easier time. Equivalent of this would be Q0 is psi transpose norm M X0. And this equivalent, if you want to avoid using inversing of a matrix, linear algebra provide us with an alternative, X dot at 0. Nevertheless, let me tell you how to calculate the inverse. So reminder, inverse of a 2 by 2 matrix, right? If we have A, B, C, D inverse, does anyone remember what was the inverse of a matrix? 2 by 2 matrix. Just out of curiosity.
It's the inverse times the determinant for each.
Wait, we are finding the inverse.
Oh, sorry, the 1 over adjoint of the matrix times times something I can't remember.
All right. You know what? I'll leave it here. You guys look it up. You guys fill this in.
Wasn't it AD minus BC? Oh, that was the determinant. Oh my god.
That's the determinant.
Yeah.
But we want to find the inverse. Right? So first part, you're right. There is something else there. So it's 1 over AD minus BC and multiplied by something.
Don't you multiply that by DBCA?
Let me see what you're saying. So you're saying multiplied by A, B, C, D.
Oh, D minus B minus
B, yeah, minus C and A. Right?
Yep.
All right, yeah, that's correct. So 1 over determinant, then, well, the way you move it, I don't even know how to describe it. You multiply the off diagonals with minus and flip the diagonal elements. Just, you know, as a reminder that I guess I left too much room for. There you go. You can always look this up. All right, so now we have initial conditions. We take them from physical domain to modal domain. So we're good. We have now, remember what you were trying to do. Don't get lost there, right? We're trying, this is the equations. These are the equations in modal domain, right? The equation of motion in modal domain. And these are initial conditions in modal domain. So now we have our systems in modal domains uncoupled. So we can find the system response. So step 6. Find the, let's say, system response in modal space, right, or modal domain. Maybe I should use both. Modal domain, because I use both of them. Modal domain or modal space. You can go with physical space and physical. Physical space and modal space, physical domain or modal domain. So how do we do that? Well, now we have M11 bar, Q1 double dot plus M22 bar, Q2 double dot. No, what I'm doing there. It's a simple system. So K11 bar, Q1T is equal to 0 with Q1 0 and Q1 dot 0. And then we have M22 bar, Q2 double dot T plus K22 bar, Q2T is equal to 0 with calculator. Oh, for inverse, yeah, definitely you can. I do not care how you calculate the inverse. You can definitely use a calculator. I would actually encourage you to do that. And the initial condition would be in Q2, initial velocity, initial displacement, right? Now you have a system like this and another system like this. This is in modal domain. Now you have K11 bar, M11 bar, And the initial condition for this one is, well, this is the space or the coordinate Q1. Initial conditions are Q1 and Q1 dot. For the second system, you have M22 bar. You have K22 as the stiffness. The coordinate is Q2. So Q2 and Q2 dot. Initial displacement, initial velocity. So if two systems, you find the system response from here. It gives you Q1T and Q2T. Final and last step, now that you know the responses in modal domain, you can take them back to physical domain. Now, that's what we care about. Right? So take the solutions, I would say, from modal space. Well, let's just go with modal domain. Now I'm using modal domain. Modal domain back to physical domain. How do we do that? Well, xt, or use the transformation again. Right? Let's just take it into two parts. Let's say A, that's what I always do. If all the conditions were 0, all initial conditions were 0. I, that E, you will see that mainly, well, let's just not do it, because this is when you're dealing with force vibration. If all the initial conditions are 0, you're not going to have any vibration here. So let me just do it with the typical way that we do. So if takes it from modal space domain back to physical domain, and let's just do it in an old-fashioned way, I would say, instead of making it complicated. So xt is psi, right, qt. That we know. This is a general. We said this is a general transformation we have when we're dealing with matrix with modal analysis. Right now, because we are transforming it back to physical domain, and we transform the initial conditions to get the right initial condition modal space, we had to normalize the modal matrix. In order to take back the solutions, we also have to use normalized modal matrix. So pay attention. When you're taking it back, because we transformed the initial condition, right? We transform initial conditions using normalized matrix. Now we have to take the solutions back to model physical space using the normalized matrix, normalized modal matrix. Otherwise, you don't get the right answer. Right? Because of the dimensions have to be transferred properly. All right. So what does this mean? It means, well, this becomes x1t and x2t are equal to x1 norm, x1 2 norm, x2 1 norm, and x2 2 norm multiplied by q1t q2t. Remember, q1t and q2t are the solutions that you got from step 6, right? So you have solutions from step 6. You're good. You know the modal matrix, already normalized modal matrix. Right? This is solutions from step 6. This is normalized modal matrix. So it's a multiplication, 2 by 2 matrix multiplication, 2 by 1 vector. Gives you 2 by 1 vector. Now, the first element of the vector becomes the solution, right? The first becomes the system response for x1, better to say the mass 1, and the second one becomes the system response for mass 2. If I want to write it in a general term, this becomes this. X1t becomes X11 norm Q1t plus X21 norm Q2t. Q1t and Q2t, they are equations, and X11 norm and X21 norm are just constants. Right? You found them already. X2t becomes X12 norm Q1t plus X1 X2 norm. I was almost missing that. X2 norm Q2t. Now these are system responses in physical domain, and that's what we were looking for. You see that now each solution, you have Q1t and Q2t, the response to each mass, the way it oscillates, the way it moves, is weighted by the coefficient, some coefficient that is coming from normalized molar matrix. So although they are formed by, as we said, we can represent the solution. This goes back to what we said at the beginning. We can represent the system response using a combination of modes. Here it goes. Q1 is the response in first mode. Q2t is the response in second mode. Now, the general response for mass 1 is a combination of these two, weighted by those coefficients that are coming from normalized mass matrix, modal matrix. Sorry. Response for mass 2 is also a combination of the response to first mode and response of the second mode. Combination of those added together, weighted by, or each response is weighted by the component we get from mode shape. Now, these coefficients determine how much of the response is coming from the first mode, how much of it is coming from the second, right? For each mass response. All right. So here, that was the general process. Now, keep in mind, the reason I teach you this, because this is not limited to just a system with 2 degrees of freedom. If you have a system with 10 degrees of freedom, exact same process. The only difference is that you are going to have a 10 by 10 model matrix. You're going to have a 10 by 1 solution and 10 by 1 and 10 single degree of freedom system. In a step 6, instead of having two equations, right? 2 equations of motion. If you have a system with 10 degrees of freedom, you're going to have 10 single degree of freedom systems in model space and solve them one by one. So there is nothing new there. Everything you've learned so far, like how to deal with systems with single degree of freedom, you can apply it just in a matrix form for a system with multiple degrees of freedom. Again, 2, 3, 4, 5, as long as you find mass and stiffness matrices for that system, you can actually follow these exact steps. Here is 2, so step 6 gives us 2 equations. If it was a system with 5 degrees of freedom, you will have 5 equations. Solve each of them in a similar fashion. Each of them is a single degree of freedom, and then take the solutions back to physical domain. The only difference for higher degrees of freedom is that the matrices become bigger, and vectors become bigger. Here we have 2 by 2 and 2 by 1. 50 degrees of freedom, you're going to have a matrix of 50 by 50 and a vectors of dimension of 50 by 1. Right? So the same process, but as long as you know mass and stiffness matrices and can form the equation in matrix form, you're good. All right. So stop here.